Right, well, it's my tremendous pleasure to introduce our speaker today, which is Sergio Martin-Alvarez, who has visited us before, so we're back again. Sergio did his PhD in Oxford with Julian Devrient, and then he went to Cambridge, where he worked with Deborah Sajaki, and he's now an independent fellow spreading his wings and building his own team at Stanford. He's done lots of really important work on numerical simulations, in particular dwarf galaxies, which is a big theme also here in Surrey. But he's been looking at things like magnetic fields and cosmic rays, and we'll hear a lot more about that, I think, in the talk today. And he's also managed to resimulate one of our edge dwarfs. We're excited to see results from that too, and how that looks and pans out. And so really, without further ado, over to you.
Thank you. Yeah, so precisely one of the main focuses of my talk is going to present the first preliminary results. Well, preliminary, they're already out in the archive. Simulating dwarf galaxies with radiation, magnetic fields, and cosmic rays simultaneously. And just to basically to show you a bit of what we expect to come from the follow-up simulations that we're doing after these initial dwarf simulations. Just to go back to the typical beginnings and ease us into galaxy formation after lunch. You guys have seen this graph before. The idea is when we talk about galaxy formation, we're trying to get right the typical properties that we observe in galaxies around us. And the very basic first of the thing that we want to do is to get the typical number of galaxies of a given stellar mass to match that of observations, right? And so the idea for this is that we have, I'm already not pointing, okay, that we have the typical structure distribution of halos of dark matter that we have in our universe around us, determining if you assume all the variance in these halos to be converted into stars, what would be the cosmic baryon function of our universe, right? Which is shown here by this purple line. But of course, when you look at the data points that you have in here, this line here doesn't match it. So this is telling us that there is some mechanisms regulating the efficiency with which each dark matter halo is converting its baryons into stars. So typically, this is governed by feedback processes, and we believe in particular for the low mass end of stellar masses that this is regulated mostly by supernova feedback. And then, of course, when you go to the high mass end, then you have AGN in principle, and this dominates that regulation. And you can see that our simulations, when we include this supernova regulation and this AGN regulation, tend to match observations really well, right? However, the question is it really just supernova and AGN? We know in particular there is all this physics, such as radiation in the form of stellar radiation, included by radiative transfer. Cosmic rays are becoming a big thing these days that are missing from this simulation. So the question is, why are we getting the actual answer so right when we are missing some physics? And the reason behind this tends to be calibration of the numerical parameters of our models. In particular, for example, you can see this work of Matthew Smith a few years ago now, where he just simulated the various dwarfs, and you can see that typically if you believe the abundance matching predictions, you would expect your dwarfs to fall down on these relationships down here, but his simulations are showing that at least with the conventional physics, with the conventional configuration, your systems are too massive in terms of stellar mass. There is a solution for this. So for example, these Sphinx simulations, which I'm going to be featuring quite a bit, they use the calibration of feedback by a factor of 4. And the reason I'm showing these particular simulations is because they have a somewhat similar setup in terms of radiation or radiative transfer to what I'm going to be using. And the objective of this factor of 4 was to just get the prediction that you would have for the halo mass, stellar mass, from dwarfs around us that Justin did a few years ago. And also maybe if you want to extend the abundance mass into lower masses, then you can also see that you're trying to match that, right? Again, with a factor of 4, boosting the strength of the supernova feedback. Yoki is not the only one. There's many others. We've all done it at some point. You calibrate your feedback, Nihal, fire, any simulation you go out there, basically has to calibrate some parameters to get these values right. And when we talk about calibrating the feedback, the question is, especially for those in the audience that maybe are not running simulations, what are we actually doing, right? So when you run with no supernova feedback, what you find is that your galaxies, of course, are extremely massive in terms of stellar mass to completely unrealistic values. Then you can regulate that a bit with the fiducial standard vanilla numbers supernova feedback. But if you actually want to get a significant suppression in mass and you boost your supernova feedback a lot, what you get is, again, this desired reduction in stellar mass, but then a system that in terms of temperature, in terms of gas, you can see a lot in the actual video. There's just the density of the gas shown in blue, and then the temperature in red. And you can see that the galaxies accreting gas, forming stars, blowing it all up. Then it falls back into the galaxy. It has this kind of like breathing pattern Whereas the other systems are already forming disks. This one is just a total mess, right? Where the gas is just flowing in and out. So you're sacrificing the appearance of your galaxy when you calibrate your feedback as a compromise to get the stellar mass right. So this is going to affect your properties, and it's going to affect how you fare when you try to look at different observables and how your systems compare with observations. And in particular, when we go to dwarf galaxies, we know that lambda CDM has many open controversies. You have to fail, cast core problems. But then on top of all these problems that you want to solve, you also want to get your dwarfs right. So sure, there's the stellar mass, but you also want to get morphologies, the amount of metals that you have, times at which your galaxies form. You want to get all of this right. And in particular, when you go to kinematics, for example, you find that, again, feedback calibration is not enough, right? So you can look at the diversity, and I like this work quite in particular because what they show in here is that you not only not get the dwarfs, like the galaxies right, but when you actually get your galaxies right, you don't get the distribution of the properties of the galaxies to, right for a population, right, with just feedback calibration. And they try different things. They try fiddling with the models of the parameters of the model, sorry. They try including dark matter alternative models, and none of that works. And if you just go to the literature, you're going to see that your galaxies are going to fail. Your dwarf galaxies are going to fail in terms of metal enrichment, morphologies, kinematics, for many other works. So these properties are all giving us a challenge in terms of how we model our dwarf galaxies. But again, we are missing a lot of physics, right? So maybe the solution for this is, instead of fiddling with our models, we just want to put the physics that we are missing, and hopefully this will help us. And of course, life gets in the way, and you not always get to the point where you can include all this physics that you want. Calibrating feedback is a useful mechanism to get realistic galaxies that we can use as an ensemble to just study populations. But some of the things we are missing, and these are the ones that I'm going to be studying here, are to start with stellar radiation, which we know for a fact, that is the biggest contributor from stars in terms of integrated energy into the ISM, but that's not perhaps the most important part. One of the very interesting things that, including radiation, that is that it preprocesses the gas where supernova events are going to take place, which implies that then your supernova events are more effective taking place in colder and in more diffuse environments. Radiation can also help you by porting the accretion onto systems or into galaxies, by evaporating the inflows. And we know that in isolated simulations, for example, it can drastically reduce the stellar mass of your dwarf galaxies and also drive outflows, even though actually the outflow side of things with radiation is becoming quite controversial because there is work showing that it might increase the amount of outflows you can generate from galaxies. It might decrease depending on the setup. So that's not fully clear at the moment. And it might actually lead to some sort of positive feedback where actually radiation leads you to have more stars instead of less stars. I think that's kind of open these days. But there's other components that perhaps have a bit more of a more clear effect on what's happening with your simulation. So for example, magnetic fields, there's a lot of work on this area in the few past years, but it is still not, we still haven't reached models that we're fully happy with in terms of magnetism. However, we know that including magnetism is going to affect the ISM appearance of your galaxies. You're going to get galaxies that are going to look smoother, and you're going to have more organized motions. You're going to have thicker disk when you have these galaxies. When you look at the multi-phase structure, you're going to see that the actual different phases are going to be distributed differently across your disk and also in terms of height. And then in particular, when we know magnetic fields are extremely important is when you go to star formation. So when you go to the smaller scales, magnetic fields in the form of the effect on magnetohydrodynamical turbulence by providing more solenoidal motions and providing support against collapse are going to affect how efficient you are in forming stars and the distribution of this. An interesting thing on top of this, when you actually include magnetic fields in your simulations, that you can now go to all these radio and far infrared observations, and you can see if your simulation matches those properties as well. So it's opening a new domain of actually comparing with observations. In particular, because SKA is around the corner in principle in the next 10 to 50 years. And at least it's one of these are going to explode, right, when it's sending up to space. But it's going to give us a lot of different observations to compare with in terms of magnetic fields. But there is one very crucial aspect in terms of why magnetic fields are important. And it is that if you want to model cosmic rays, which are the new fancy, sexy thing in the room, you need to have the magnetic fields, right? Because magnetic fields determine specifically how cosmic rays propagate and the dynamics of these cosmic rays. So why do we want cosmic rays in simulations? Well, one of the things that we've been struggling for, especially more massive galaxies in terms of simulating the systems, is getting continued more temperate winds, right? When you have supernova driven or AGN driven winds, what you have is these very hot outflows that are very explosive and are very eventual. They don't take place continuously. So if you have cosmic rays, in principle, the theory was you can establish a smooth pressure gradient due to the cosmic rays present that is gently pushing the gas out of the galaxies. So that helped us drive it out. And then, of course, when we did this first experiments with cosmic rays, not like this is in particular Marian Sparks' work, but there's many others. On top of finding this effect on driving more and more and stronger outflows in your systems, what you see is that the ISM of your galaxies is also affected. So you again, it has a similar effect to what the magnetic field did in that it also generates a more diffuse ISM and it gets rid of the denser regions in the systems. And then finally, again, we can go back to this loop of affecting the magnetic fields on top of the magnetic fields affecting the cosmic rays. So yeah, these are the three pieces of physics that I think are quite important. Of course, you're gonna say like, Sergio, you are missing all this other stuff that we know is quite important, right? So of course, yes, in these simulations, I'm not gonna have supermassive black holes, I'm not gonna have AGM feedback, I'm not gonna have thermal conduction, there's many other things, of course, still missing from our simulations. But these three are important. So maybe to give you a bit of a background of how we model this in Ramses, and also about the caveats of the modeling. So we're using this implementation of cosmic rays in Ramses by Johan Dubois in the last 5-ish years. He's been working continuously on this. And so what we're doing here is we include the cosmic rays as an energy term that is separated from the other terms, which is allowed to be advected in your fluid based on the local properties of the magnetic field. And this is solved with an implicit solver, which is quite expensive, but it allows us to model the streaming of cosmic rays, which is generally missing from the other modeling. And I'll tell you in a minute why our models for cosmic rays are not that good. Then you can couple that with the magnetic field and with the energy equation, and that works pretty well. However, when you introduce cosmic rays, you have new parameters in your model, which means more degrees of freedom, more calibration, blah, blah, blah. So one of the very first things that you have to worry about is the actual amount of energy of cosmic rays. So we believe in principle that cosmic rays are mainly injected into our galaxies through supernova events, right? The actual shocks accelerate these cosmic ray, very energetic particles. How much cosmic rays you actually inject in your simulations is not certain yet, but we know for roughly that based on theoretical predictions and the actual observations that we have on cosmic rays and supernova remnants, it shouldn't be more than 20% of the actual energy of the supernova. Typically, people settle on this 10%. And if you go through the literature, pretty much all of us are using 10%, but we don't think that's going to affect things too much unless you go very low in terms of going to 1 or even below 1. However, this is the little order, right? The diffusion coefficient. So these numbers here is basically going to tell you how do your cosmic rays couple with your systems in terms of scale. The larger the number, the larger the galaxies are going to be affected, or rather, the larger these scales that you're going to affect with your cosmic rays. So these numbers are expected to range between about just close to 10 to the 27 up to about 5, maybe even higher, 10 to the 29 centimeters squared per second. This is based on local observations of the gamma rays, hadronic losses that you have in the Milky Way, the spallation of cosmic rays, and so on. And you can see that these observations tend to range between 10 to the 27 to 10 to the 20. So for this work, we really try, and this is the case for all the parameters that I'm going to show in a minute as well. We try to choose something that we think is realistic, and if our galaxies end up being just completely wrong, then so be it. We're not aiming to calibrate anything. So that's the reason we choose a number that sits a bit in the middle of the interval. There is more caveats in here, though. One of the important things and the problematic things is that the reason observations give you different numbers and that's such a broad range for this number is that how much the cosmic rays diffuse in reality is a local quantity. You cannot use a fixed set coefficient. But that's one of the things that we need to include in our models in the future. And then also the fact that cosmic rays have different energies, and depending on the energies, the diffusion of these particles is going to be affected severely. There you go. But overall, at the moment, most of us are just working with these set numbers. So it's just a bit of a caveat that I want you guys to bear in mind. So again, to model cosmic rays, we need magnetic fields. If you're using Ramses, you're in for a treat because the magnetic fields are a pain. But then one of the good things is that we have constrained transport. That implies that we are solving the magnetic fields solenoidal constraint down to numerical precision. That means that your magnetic fields are not, they don't have any monopoles at all. And so one of the cool things is that you can see this for multiple simple tests. Whereas if you go to other methods, they start to include some divergence. And in particular, you see, for example, for divergence cleaning here, which is just instead of making sure your magnetic fields are non-monopolar by construction, whenever you have monopoles, you try to push them away. And you can see that in particular, for example, for the Powell divergence cleaning method, in very simple problems, such as the affection of a flux, of magnetic flux in a loop, it failed catastrophically. And then you also can see in very simplified problems that there are differences in the appearance of your simulations. This is bad because when you actually go and look at what is the actual relevance or the strength of the magnetic monopoles, compared with the local strength of the field, with constraint transport, you're talking about median or average values on the order of 10 to minus 15, so definitely close to 0, and maximum localized values in your simulations that maybe at sometimes approach being 1% of the magnetic field strength. However, with other methods, you're going to find that your divergence is on average around 40 or 50% of the strength of the field. So 50% of your field is monopolar on average. I don't want to see what is the highest numbers that you get. And so what happens, for example, in these simulations with a red ball with these two methods is that you see the divergence cleaning and the constraint transfer method yield magnetic field strengths are extremely different, right? That's what you see in the bottom panels here. And this even affects the actual density of your galaxy. So you really want to go to methods that are accurate, or at least basically benchmark against them. And this is not something that is brand new. This has been known since the 90s. There's a lot of work by Balsara and also Todd that shows you that your divergence cleaning, sure, you're never going to get things right in these continuities, but your divergence cleaning method inject conserved quantities. So conserved quantities are not conserved. So this is a bit of a problem. Whatever, this is not important. But the crucial aspect in here is once your divergence is not known, when you go to your induction equation and check how it affects the evolution of the energy, so I'm just multiplying this by another magnetic field term, you're going to see that this term is not 0 anymore. And now, driven by the velocity, you can use a monopole whenever there's a velocity flow through it. You can just extract magnetic field or magnetic energy out of the kinetic energy ad infinitum, right? And nothing's going to stop you from that. So this is something that we need to be concerned about. So that's a good thing for in particular, these simulations. Again, magnetic fields with constraint transfer. I'll stop with the numerics in a minute. Just going through a bit of the setup. The idea here is that we're simulating the same dwarf, the same galaxy, with different combination of different physics. The galaxy formation methods are, the vanilla is pretty standard, but then when you go to the specifics, our magnetic fields are either seeded by supernova remnants, so basically trying to generate an astrophysical injection of magnetic fields, or ab initio, which means that they're primordial and they were there at the beginning of the universe. Our radiative transfer is very similar to the Sphinx simulations. I'll mention a couple of things in a minute. And then, as I mentioned, for cosmic rays, diffusion and streaming, fixed coefficient sitting in the middle of the range that you expect. We use this magnetothermoturbulent star formation prescription. That means that our star formation is local. We look at the local properties of the gas, whether the actual magnetic, thermal, and turbulent support are able to overcome the gravitational pull of the gravity of the gas. And whenever that happens, we use an efficiency for the formation of stars that depends on the local properties of the gas. Whenever we form star particles, we allow these particles to generate stellar feedback. The idea behind this actual method is this Station-Skim's method for supernova explosions, and is that it uses the standard set of Taylor solution whenever we don't have the resolution, and we shift to a momentum injection whenever we actually need to just capture the injection of energy more properly. Whenever we have stars, there is stellar feedback as well on top of the supernova feedback. Radiation in 3 bins, we can ionize hydrogen, helium-1, and helium-2. Again, the standard Sphinx setup, and then you can also inject magnetic fields. We use 1% of the energy of the supernova to go into this budget whenever we have this injection, which implies that we're magnetizing our remnants to the expected magnetic fields. Right, so we're getting the right solution by default on small scales. Yeah, sorry, go ahead.
Sorry, just following on this, does that mean that 0.9% then goes in the thermal?
Yes, exactly. We in these cases, so for magnetic fields, we're going to the down pointing like 0.99.
Yeah.
And then when you have cosmic rays, you go down to 0.9 or 0.89. You have yes. So the actual amount of energy is conserved, the total, but the thermal energy is just being reduced. You'll see in a minute that they actually, like, you don't lose an impact, you get a higher, stronger impact, based on why cosmic rays are quite efficient in the systems. So we are simulating this dwarf galaxy. It was originally an Arepo simulation setup, so that means that our zoom is slightly bigger than usual because they really struggle with contamination from particles. We have this very little dwarf. They don't really struggle. It's just that you have to be more careful with these kind of methods compared with grid methods. We have this very little dwarf in the very center of our halo, just forming here. You can see how we zoom in slowly, and you can see the system in the center. This is the run with radiative transfer and cosmic rays. And you can see this nice bubble where the actual gas is being pushed out in blue. In general terms, the zoom is again fairly large, 0.70, about 0.7 megaparsecs moving in radius, so a bit larger than that. For a fairly little dwarf that we resolve with about 7 parsecs per cell, full cell size, and then a stellar mass of 400 solar masses for the dwarf. So once we simulate this, we get a few new physical quantities in terms of magnetic field and the cosmic rays. Now we can also combine with the ionization fraction of hydrogen to construct, in the future, we're working on this, far infrared observations, but at the moment we already have some pretty cool, I would argue, radio smoke emission for these galaxies. We have a lot of simulations, but the overall theme down here is that we have some no feedback runs just to check what the different star formation models are doing. Some different feedback runs, which are calibrated with the higher strength and not with different also star formation models. And then we start to get into the actual interesting side of things. We have a few different magnetic field models, and then we combine those with radiative transfer. And finally, we have some runs with cosmic rays and MHD, or cosmic rays, MHD, and radiative transfer, which we separate with streaming and no streaming, but not much of a difference here. We'll see that streaming is actually not that important for these galaxies. So if you guys just try to remember a bit the color scheme for this, like basically that doesn't show too well, but blue is no feedback, red is feedback, standard typical different feedback runs. Magnetic fields will be in purple, then you have RT in these orange, brown colors, and then cosmic rays in green, because I'm going to try to keep that palette consistent. And so the question is, can we form realistic dwarf galaxies by including all this extra physics? So the very first thing I'm going to do is I'm going to look at the stellar mass halo mass relationship, which I'm going to just slightly reframe in here to be the efficiency of conversion of baryons of gas into stars by dividing by the halo mass multiplied by the fraction of baryons. And then I'm going to plot the same simulation at multiple times, which means that you're going to see the halo evolution over time on the x-axis. And I also have the Bernoulli extrapolation. This is widely extrapolated just to give a bit of a broad idea of where things are sitting at compared with that. So again, no feedback, it just drives your galaxies to become extremely very massive. When you include feedback, however, you start to see interesting things. So the very fiducial simulation, and Deborah likes to call this the ninja star. You're gonna see this funny symbol sitting around for a long while. This one drives your galaxy in terms of suppression of stellar mass to fall on top of Bernoulli. This is not necessarily a good sign. It's just telling you that the stellar masses are on that order. And then when you calibrate the feedback and you increase the strength of this feedback, you get the suppression of stellar mass by a factor of about 5. We can add more physics on top of this, see what happens to the actual stellar mass of the system. So when we start with magnetic fields, we see 2 different possibilities. So at lower redshifts, let me just point this out at the moment because I actually forgot to mention this. Most of our runs, we only evolve to redshift 3.5 or 3.3 actually, because these become extremely expensive with cosmic rays, so we just really cannot get much further than that. But the galaxy is extremely isolated, and it doesn't evolve much between redshift 3.5 or 3-ish down to redshift 0. So you can see that in the runs that we expand to redshift 0.5, and you can see that the actual stellar mass doesn't change too much. There is some amount of star formation, but it's very, very small. So that you can see in this one here and this one here. Of course, without feedback, this keeps forming stars forever. So going to what magnetic fields do, there is 2 different trends here. One is this one here, which are extremely strong primordial fields. These things are just, basically you have a universe full of rubber bands everywhere, and this suppresses and delays star formation early on and has a bit of an impact all the way through. But these values are quite unrealistic for the primordial field, and I'll try to show that later on with a different set of simulations. On the other hand, on the other side of things, what happens when you actually have more realistic numbers, both in the form of injecting fields with supernovae and having a primordial, relatively normal strength field, is that once you collapse your system and you start forming stars, you start to get some support from the magnetic field, and you get these extremely large molecular clouds that are supported by the magnetic pressure and cannot collapse until the point they become critical, and then you just have the entire cloud collapsing and becoming stars, followed by extremely strong feedback that just effectively halts star formation any further until lower redshifts. This is not a realistic effect. And the reason is that my simulations were missing up to the inclusion of radiative transfer. They were missing early feedback from stars. So what this means is you form your stellar particles and they do not affect their environment until few mega years afterwards, these particles explode as supernova. Of course, this is not what happens in reality. If you have, for example, radiative transfer, or if you have stellar winds, which these simulations do not have. I should add that to my list. What happens when you have these scenarios that after the formation of your stellar particles, the feedback from these particles can hold star formation longer. And that's what you see up here with these radiative transfer simulations, is that early on, the actual radiative transfer is just inhibiting the formation of further stars. And then as time evolves, you'll see that our galaxies slowly catch up by having a very continuated amount of star formation. We can combine that with magnetism. And what happens now is that you have this extra support before you form the stellar particles, in particular, in this case, with the very strong primordial fields. And then you keep the galaxy formation of stars quite inhibited until you have a system for this particular one, in this particular case, with the very strong fields, that is extremely gas rich. And then suddenly you cannot stop the formation of stars anymore. And the other problem that you have is that these particular very strong primordial fields are wrapping the gas around the galaxy. Whenever the feedback tries to push out of the galaxy, it has to beat the magnetic pressure of the environment, and it confines the gas into the galaxy. And therefore you end up with a system that is actually quite overmassive in terms of gas. So we're hoping that this help us further roll out these very strong primordial fields, which are well within the constraints that we have at the moment. But then we forget about those then from now, and what we're gonna see is when you have injection by astrophysical sources, the actual additional support that you get from the magnetic fields combined with the radiation is going to lead you to have, once you form stars, you're going to form more stars or more concentrated stars. You're going to have, again, this explosive feedback, now combined with a higher concentration of radiation in a given region. So that is helping our galaxy to inhibit star formation for a longer period. And quite funnily enough, if you look at this, we're actually getting an effect that is quite comparable to the boosted feedback with the factor of 4 from strings. However, at the redshift about 6, 7, we find that gas starts to collapse into our galaxy and we cannot beat this anymore, and we start to form stars again and go back into the main track where all of our galaxies are concentrated. However, we still have an additional component, cosmic rays. And so the idea behind cosmic rays was that you need to build up a gradient or a profile of pressure that has a defined gradient decreasing outwards that's going to help provide support. The problem is without radiative transfer, there is nothing to do because you already form your galaxies by the time you build up this gradient. But when you have radiative transfer, you're allowing the cosmic rays to build up an impact. So initially, they're not that important, and you can see our simulations with streaming and without streaming, which again, doesn't make much of a difference at all. Just follow the magnetic fields and radiative transfer runs down to this low redshift, this redshift of 6, 7, and then they continue inhibiting star formation down to redshift of about 5s. What we have seen here, and you'll see this in the gas budget, is that the cosmic rays are pushing more gas out of the system. However, in particular, our galaxy has this annoying merger at about redshift 5s or so. And when this other galaxy comes in and merges with the main dwarf, we actually find that it provides enough gas to just again form stars. And we just can't get away from this kind of locus for most of our simulations. You'll see there's 2 different paths for the streaming and no streaming run. This is just based on the properties of the merger. And I'll talk about the mergers in a bit more detail because it actually changes quite a bit one of our cosmic ray simulations. So we can compare with other things. And one of the things that I've been quite excited for a while to compare with was the actual Sphinx simulation. So at redshift 6, we can compare with the spread of the masses of the Sphinx galaxies. And you can see that our models, sure, they're all well within the spread of the Sphinx, but in particular, the Sphinx uses this factor of 4. They calibrate on the stellar mass, not on the reionization history, and they get the reionization history extremely brilliantly. So when you look at this graph, we're hoping that we can get the right stellar masses with cosmic rays, and then get the right reionization without any need for calibration, if you trust this. Of course, there's been more work on the Sphinx side of things that we're actually seeing at the moment that, sure, you might get the stellar masses right, but the cosmic rays are ruining the reionization by making the galaxies more opaque. So that's a new problem. The other thing we can compare with is the actual observations or the estimates for the halo mass, stellar mass from galaxies around us. Again, Justin is quite familiar with. And so the idea here is that we get some typical values for the stellar mass of the dwarfs around us for a given halo mass, and in particular for our system. And you can see that for this particular system, the values without the boosted feedback tend to fare better than the values with the boosted feedback. This boosted feedback will become quite successful in some other observables. However, at high redshift, and of course, big caveats here, because this system is a redshift higher than 6, it's pre-reionization, so the physics at play are very different in terms of galaxy formation. But if we want to approach these lower stellar masses, we can only really get close to it at all with the boost of the feedback or the cosmic rays. So this is helping us get significantly lower masses at these higher redshifts. Again, these galaxies that we observe around us are post-reionization, and this system is pre-reionization. So there's caveats in what's going on in here. But in particular, the nice thing, if you are interested in this comparison at all, is that the cosmic ray simulations with radiative transfer are the ones that approach the most the lower halo mass stellar masses and the higher stellar masses, right? So this is at the bottom sort of things, which we found quite interesting. I'm not going to talk about this. So sure, okay, stellar mass is an interesting diagnostic to try to match observations of galaxies around us, but there is many others, right? And this is when we want to get into actually getting galaxies that look like the observation. So one of the things that you're going to try to simulate to reproduce next is the actual kinematics of stars. So what I'm showing these two panels on the left is the typical rotational velocities of the rotational velocities of these stars in our galaxies and the dispersion of these velocities. We are interested in particular in comparing with the cyan points that you have in the observations, which correspond to isolated systems around us. And you can see that overall, most of our models without our radiative transfer have rotational velocities that are quite considerably lower compared with the ones with radiative transfer. Sure, magnetic fields seem to also be sitting down up here, but we'll see in a second that that slightly changes in other observations. So again, radiative transfer, cosmic rays, no cosmic rays, whatever is helping us match these things better, maybe magnetic fields as well, whereas these models are failing somewhat in the rotational velocity. However, when you go to the actual dispersion of stars, of the velocity of stars, the boosted feedback models are the ones that can actually match the observations. And then if you look at all the other ones, you can see that they're, I would say, I'm happy to say in tension. Some of the co-authors prefer to say in slight tension. I think if you want to sit at 10-ish, 20 is a bit bad. But here, if you actually look at the runs with radiative transfer and cosmic rays, these are the ones that have realistic values. And in particular, this one is sitting, in my opinion, still at some degree of tension with the observations, but way closer. So this is approaching the success of the boosted feedback here. And then we have this other run up here that was sitting down, way down. But again, there is this merger that this one is particularly damaging to the system, and it makes it way more concentrated. You'll see in a minute. This also reduces this merger reduces the size of this run and increases the dispersion of velocities. So it has significantly affected the structure of the galaxy. If you look at this prior to the merger, this is also looking fairly similar to the no streaming case. And then again, if we look to the actual support, whether it is rotational or dispersion dominated for the stellar component, you can see that again, there is this divide between magnetic fields and radiative transfer and the other ones in here. So we get something that is a bit more rotation dominated with MHD or with radiation. When we look at the morphology or the size of the system, I think I'm just going to focus today on this panel because I want to show some other things later on. But we can look at how the actual mass size relationship compares with observations. And overall, if you see that the observations are sitting in this kind of line up here, you can see that most of my simulations tend to have galaxies that are a bit too small or quite small compared with the observations. Again, the boosted feedback is doing quite well because not because the galaxy is bigger, but rather because the expected size for those stellar masses is smaller. However, if we go to the range of simulations that we're interested in here, where most of the runs are sitting, we can see again that the fiducial model is failing, but if you include radiative transfer and magnetic fields, you get something that is slightly more extended in terms of stellar mass. And we believe this is because you have more clumps in terms of our measurement of the size. You have more clumps of stars that are just more distributed radially. And then here, the radiative transfer and cosmic rays runs are also sitting in this distribution. You can see in this one particular graph, this one here with cosmic rays streaming was sitting up here as well in terms of size, and then it merges and it just goes down. So this merger is kind of ruining us. You can be skeptical if you prefer. I just like to announce it because we really think that the cosmic rays are helping in the properties, but the merger is significantly changing the galaxy. this effect on the actual galaxy is also transferred to, for example, resolve kinematics. So one thing that we see in general is that if you have the hydrodynamical run, everything is looking quite smooth, and you have clear rotation patterns, and in particular in the gas, whereas maybe not that much in the stellar component. But once you have cosmic rays and radiative transfer, you get misalignment between different components. In particular, it's interesting to see misalignment with the H2 and the H1, which is quite indicative, or people have thought that was maybe indicative of AGN activity in these galaxies. You can also attain this with cosmic rays. And radiative transfer seems to, in agreement with the other graphs, gives us a bit more of a clear rotational structure in the systems. Another cool thing is that, of course, when you do a hydrodynamical estimates for the ionized H1, the ionized hydrogen or the neutral hydrogen, you have to actually just predict this post-processing, whereas we have this properly done on the fly. And one of the last things I want to mention for the dwarf is what's happening with the actual density profile of the system. So when we look at our galaxies in terms of the cusp core problem, what we tend to find in general is that most of our galaxies have extremely cuspy profiles on the dark matter. So that's the reason we just have these arrows pointing upwards. They're just even out of the range of the plot. But if we look at what's happening with our fiducial runs, with and without boosted feedback, we see again that they're quite cuspy. And only when we introduce radiative transfer, we are able to find things that are starting to shift down in terms of the dark matter density at these 150 parsecs diagnostic that Justin introduced a few years ago as well. It is with cosmic rays and radiative transfer that we, for the first time, are actually having simulations that are approaching the core-like model prediction for these densities. However, again, when you go to look at this run, and again, honestly, you can be skeptic, but we have this merger and we find that prior to the merger, our galaxy is sitting very nicely down here, but then the merger occurs and the density profile is just bumped up in terms of the dark matter. So overall, we would argue that this is helping our galaxies. Cosmic rays and radiative transfer are helping our galaxies get more core profiles for the density. Also, something else in a minute related with that. Another thing I want to show, this is me trying to criticize Justin's work a bit, but it didn't work, it didn't go up too well. So we were quite skeptical of the idea that just measuring the density close to the center of the galaxy was a good proxy for the actual cuspiness of the profile. But one of the funny things was, if you look, for example, at the hydrodynamical versus the RTCRMHD simulation, you see that the system that has a more cusp-like density actually has a more cusp-like profile. So we couldn't get too far with the criticism, right? Whereas this one here that is sitting at the core-like density is actually fairly flat compared with this. So it seems to be actually faring quite well for a galaxy. Again, one galaxy. I'll try again with a different one. Just to illustrate a bit, I've been talking about this merger. So here you can see the evolution of the simulation that is just doing this funny down and up. You can see that the profile of dark matter, or the densities in general, is quite flat towards the center. Sure, here. But it's quite flat in terms of density. It remains a bit like that. But then once the merger occurs, there starts to be this trend was concentrating the galaxy and compressing the galaxy towards the center. So it's the merger is just basically dissipating a bit. And eventually by redshift 3.5-ish, but this goes on to 3.3. In particular, redshift 3.5, you get this very cuspy or much more cuspy profile driven by the merger. So this merger is really ruining us in terms of what's happening to the simulation. Why is this happening? Well, star formation, right? Like the star formation is the main driver of what's going on with your density profile and how well it couples, the gas couples in the feedback with the dark matter. So overall, if you look at even just looking at the average, which is showing in the continued more space lines, you can see that once we introduce in particular MHD and radiative transfer, which is the dark brown line here, instead of having a line compared with this red one that is fairly continuated, you start to have a bit more of a variation over time. And in particular, the cosmic rays give you this more peaky and cyclic star formation. And you can see this better in the actual histograms. It's not too clear maybe on this screen, but you can see that the star formation concentrates in peaks separated by about 0.4 gigayears. Whereas if you look at the red histogram here, there is a bit of a continuum star formation. So we think this cyclicness is behind the more effective driving of the core or more core-like profile. So I talk a bit about outflows, but there is so much work on cosmic rays that you can maybe just look at that. Like, I'm happy to maybe show it in a minute, like afterwards. But I just want to also show the metallicity was also one of the very nice, interesting diagnostics for how the different models separate. And in particular, we're fairly happy that, again, radiative transfer and cosmic rays are doing much better than the calibrated feedback models. So this is kind of encouraging in terms of what happens when you include more physics in your simulations. I was going to talk about radio, but maybe not. Let me just quickly jump. So we had some problems with the actual distribution of computing time for our new simulations, and luckily this drove us to actually grab the EDGE Dwarf and repeat the same experiment down to redshift 0 with the ultra-faint simulation. And I'm showing only these lines down to redshift 3 because the stellar mass doesn't change at all down to redshift 0. I have the graphs I can show you if you want. But I just want the actual resolution. So what you're seeing up here in these different panels, I know the resolution is not too good. It's just the 9 models that we've decided to go with for the final production run, right? And here, what we're looking at is the hydrodynamic, boosted and not boosted feedback, radiative transfer, combined with MHD and then cosmic rays. And so if we just focus on the stellar mass and what's happening at the end of the life of the dwarf galaxy, no feedback again, just does its own thing, just completely produces stars. And then we have the runs with MHD and hydro just sitting here in combination. So this doesn't seem to affect this galaxy too much. Once we include radiative transfer, we find a suppression on the stellar mass, we believe. We haven't analyzed this yet, so maybe, Justin, you can give me your impression on this, but the early feedback we think is just suppressing the stellar mass a bit, not by much. The calibrated feedback, significantly large impact, again, because you have these extremely effective explosions. And then when we couple the radiative transfer with the cosmic rays, again, we get a suppression of the stellar mass, but now it's actually very significant. And it's sitting down here. So you can see the 2 runs in green are slightly different by a factor of 2 actually in terms of stellar mass. One has streaming, one doesn't. We still think that the streaming is not making an impact. We wish it didn't make an impact. This could be just be due to the actual bias between the different runs, but we're not sure about that. And the reason we think the cosmic rays are coupling so well with the radiative transfer is because you have a more diffuse medium, which implies that your cosmic rays have more gas. The lower the density and the more diffuse the gas is, the more your cosmic rays gradient of pressure is going to be able to push this gas away, because this gas is just more susceptible to the acceleration that is expanded over space. And if you also have a more extended gas profile in terms of the size of the galaxy than the cosmic rays, again, help you pushing outflows out of the galaxy. So that's the reason we think this particular combination of physics is really important for dwarfs. And then the last thing, I'm just not going to show too much, maybe just the masses in a second. The last thing we're doing, and this was the intended experiment, we're simulating a large volume of a large box. It's relatively low resolution. This is down to 20 parsecs. And we're going to have these very massive galaxy forming in the center. And we're going to take this down to redshift of about 0.8 or so. We should be quite comparable with many observations, in particular of outflows based, for example, in the Clever measurements and the Clever instrument is surveyed 4 galaxies around us, spiral galaxies. So you can see, with more detail here in the hydrodynamical model, what the little baby looks like. And again, you have the other galaxies and system in the environment around us. So this zoom is about, I think it was like about 8 megaparsecs in one direction. It's a bit narrower in the other direction, because we really wanted to go for a no pollution approach here. But that also gives us in terms of the actual sample of galaxies, quite a few massive galaxies that we can study in the zoom. And so the idea behind this is that now we'll have, using UFD from EDGE, the dwarf galaxy that I'm showing you, some work that a student in Oxford is doing, and this particular galaxy will have a quite nice spread of masses to study, where you can see that the different physics significantly affect the galaxy. In particular, cosmic rays are produced in a galaxy. If you just look at the red in the upper plots, the cosmic rays are produced in a galaxy with an extremely cold or way more cold, temperate environment around it that is still driving outflows. And so when we look at what happens in terms of physics being important at different scales, you find that again, cosmic rays are not important in dwarfs unless you couple that with radiative transfer. And then when you go to more massive galaxies, cosmic rays become important on their own effect without the need for radiative transfer, which is also kind of in agreement with the previous work that you say in that cosmic radiative transfer is particularly important in these modest galaxies. And yeah, just to maybe not take too much time, I'll just go back to the conclusions. There is a paper out on this. You can check it out for this particular dwarf. In general, we would argue that the standard physical models for feedback is not doing that well, again, to compare to generally realistic galaxies, even calibrated. But when we include these additional physics, we think it's taking us in the right direction to form more realistic dwarf galaxies or galaxies in general. So it's quite encouraging that having more physics helps take things in the right direction. Anyway, if you want to see the paper, it's in the archive. And if you have any questions, I'll take them now. Thank you.
Any questions? Questions? Start us off with one. Yeah, so I have many questions.
I'm sure you do.
I'll do one of them. So I think long ago, we were talking about how one might try and detect these primordial magnetic fields.
Right.
And I was curious how far you go from before you hit primordial gravitational field strength, and whether dwarfs are a good place to look for these things versus more massive galaxies. I don't know if you ever had a chance to look at that.
So I haven't done this for dwarfs. I done this for a large spiral, and it was very encouraging. It wasn't looking good. But exactly, dwarfs might be very interesting for this. So that's one of the things I really want to do in the isolated paper. This is get very isolated.
Yes,
This one here is a bit it's not. There's a bit of a film down there, so it's a bit harder to see.
yeah, because my intuition was sort of twofold. One, when you get to these ultra faints, they're not rotating, so you have less dynamo effect.
Right.
And then two, they're really thinking anyway, and they're isolated. So maybe you don't have to go too far, and then you could craft a whole exciting new way to probe primordial gravitational fields by looking in voids.
So yes, I mean I need to look into that. That's definitely very high on the list. I haven't looked at it yet.
I'm super curious about that. Something else to do with the edge then.
If somebody wants to do it, I'll take any help.
Violet.
Yeah, sorry for missing from the beginning. It probably a bit of what you're doing, but I'm quite interested in what sets like velocity described in this spiral galaxies. So I'm just wondering, in these kind of galaxies, have you looking at what is it that sets the velocities for like gas versus the interaction versus some of the mechanisms?
Was the expression of the gas component or the stars?
No, the stars.
Okay, the stars.
stars.
Yeah.
So you flashed a thought, I think.
Yeah. So overall, like this is just driven by the actual gas universe, right? How these stars are being formed in terms of what are the properties of the gas component. For these dwarfs, it really seems that basically whether the gas is more rotation dominated is determining most of this. Exactly, yeah. I couldn't say much more beyond that because we just looked at the quantity and that was pretty much it. I mean, we look at how it distributes spatially.
Also, it was different between when you included, sorry, the cosmic rays and
Yeah.
so it was different. So what was it? I mean, was it different?
So you meaning here? Yeah. Okay. Like these one.
Yeah, just in the bottom left.
Right. So. Okay. Right. But yes. In particular, the cosmic rays have this nice effect that they just make everything. You're imprinting the radial profile of pressure that is just continue and it doesn't disappear. It doesn't, heat to like radiate away as the thermal energy. Yeah, so it just tends to slow down the motions within the galaxy that are not radial. You still maintain, actually the radial motions are still fairly slow.
So when you say
Specifically.
radial, you mean like changing radio.
Like centrally.
Yeah.
Yeah, exactly. So you have, on average, you have a more radial motion, you have more outflows. But the actual velocities just tend to be slower because the cosmic rays are just puffing up everything and just making it more gentle. Tends to be similar to what magnetic fields do, but the problem with magnetic fields is that they drive things to, like, they just take away angular momentum, and now everything's closer to the center, and now everything's just moving fast. So that particular case, it's a bit of, again, the same more diffuse effect, but now everything's puffing up. So that I believe is behind the difference that we see. I don't know if this applies to all systems in the same manner. Yeah, I would say so, most likely.
Because you said in the simulation of the larger spiral as well.
We haven't looked at this is like right out of the oven, so I haven't looked at it. But
I still feel like it's not very well understood.
we should talk about like you can tell me maybe what is the right angle to look into this.
Yeah.
Because yeah, I'm interested in looking into this.
Yeah.
Other questions?
Hi, so yeah, Sergio, sorry. How do, so you say you see bursty feedback beating down the cusps into cores, right?
Mhm.
And then you get you get a merger wiping out
Mhm.
its effect. So what is happening with that? Are you just getting very large cuspy galaxies merging and wiping out the core?
So, right. The merging in general, I mean, okay, so this is the only galaxy where we see that conversion between a core and a cusp. I could say in all the systems, we cannot see that because the thing is a cusp already. But we have the same galaxy with very similar physics. And in one out of the two, there is a bit of more, if we look at the video, I don't have the video, but if you look at the actual merger, it seems a bit more aggressive, more head-on as well between the two systems. So we believe that's the main reason that you're seeing this difference. It's just really the merger is more head-on, the collision.
Okay.
And the gas content of the two is fairly different. Let me see if I remember correctly. So I think the one with streaming, this is seen here. Yes, that's right. This one here has less gas in the two systems, and the two systems collide more heavily. Whereas this one here has a bit less gas, and this is because there's been. This is the reason we actually are thinking we don't see a big difference from streaming. There is a slight amount of star formation going on in the system with lower stellar mass at this point, just up here. That is just it basically pushing the gas out of the neighbor. And then the two systems are more gas rich as they fall back onto each other. Because they don't have star formation prior to the merger. This is what happens in this.
Right. Sorry.
I was just going to chip into what you're saying. I guess what we're driving at though is that we know that core plus core equals core, cusp plus cusp is cusp.
Oh,
Plus
right.
cusp is
Okay.
cusp. So could it just be what's happening in the less massive galaxies that
So-
we don't see in these plots?
We haven't looked at the companion or the
Because I'd be willing to wager that it's the merger that's cored in the case that ends up being cored, and it's the merger that's cusped in the case that ends up being cusped. So it could just be whether or not you're getting a cusp core transformation in the next most massive thing. So I think
That's what I was guessing. Yeah.
Okay. Yeah, no, we haven't looked at the companion because we didn't think about we just like we see the merger just looking very different. But maybe the reason it looks different might be this.
So I've seen effects like this before.
Okay.
Where you get you get this cusp regeneration. It's in one of our papers actually.
Yeah, actually, so we refer to that.
Yeah, the idea dates back to the paper by Shervin report that's under the sorted down of these. But basically, as you approach the edge of star formation, the next most massive thing will be cuspy just because it can't form anything.
Right.
And then if that thing then merges with you, you rebuild your cusp.
Okay. Right. So that would make sense. We need to look into this.
Yeah.
I never looked at it. We're always looking at just the main, for example.
Yeah, so if something's changing in the merger, then I would look at the next most massive thing.
In terms, so the thing that puzzles me then here is that the companion tends to have this similar stellar mass. No,
Yes, but it can have
But-
different assembly speed.
exactly. Yeah.
You know, it is very sensitive.
So this is the thing that I just really dislike about dwarfs is how chaotic they are, right? Like, yeah. I was very disappointed. Like, oh, these things are gonna be simple, small, and oh, damn it.
That's what makes them fun, though.
So yeah, like it could just be a companion, just have a look into it.
So I had a couple of other quick points there. I mean,
Yeah.
I think you're doing great, by the way. I don't think you can, I mean, you said it yourself in the talk, right? I mean, these are redshift zero data points, so you can only really compare over here, and here it's all fine. What's happening over there, I think, that's, I don't expect that to match over there. And the same is true on the mechanicity and all the other plots when you've got the tracks.
Yeah.
So I think that's a sort of good news story. But the question is, in the plot where you resimulated the edge dwarf, I think, and this is where my memory may fail me, I think the original edge dwarf had a stellar mass of about 10 to the 5, which is where you're getting to with everything switched on.
Yes, I think you might be right.
So does that mean that
This
our
is-
stellar winds are somehow mimicking or compensating for the lack of RT and cosmic rays? Or is it about?
I think so. We do have. I think this is the one. Yeah, this is the one that I'm simulating. It's a bit higher than that, isn't it? Oh, sorry. I'm sorry. I thought I was.
It is whatever you tell me it is.
Huh?
It'll be whatever you tell me it is.
No, like wait. I have the plot. I have the graph for the stellar mass of your dwarf. If I can just get it. There you go. So this is the dwarf I'm simulating. The stellar mass is a bit higher than 10 to the 5. It's 10 to the
Which one of those though?
I'm doing the reference.
The blue one. Oh yeah, okay.
Yeah.
So it's a little bit higher.
It's 2, 3.
2, 3, 10.
Let me just go back to the other graph.
Yeah, okay. So it's not.
Yeah, actually, I mean, we are on here.
Yeah. So we're.
So yeah, it's
So our winds are clearly doing some of it, and then maybe there's another factor too.
so I really think the feedbacks are very different. I just remember like we simulated these isolated galaxies. It might be a completely different Oscar's feedback version. But again, like it was way hotter than the one I'm simulating. So it might be our feedback is very inefficient. Patience feedback that is.
Yeah, but it could be the winds that are.
Sure, maybe it could be as well.
Yeah. It
I
would be
mean-
fun to redo one of these with the winds.
I really think, I don't know if it is just like, maybe the winds are quite important, but also like the early feedback is. Not having the early feedback is.
Yes, and our winds are a form of early feedback. Yeah, so.
Yeah, that's right, yeah.
I think once you're down here in this band, right, then factors of 2 are really interesting, but they're certainly within the error bars of
Sure.
the data.
Exactly, so this is again, I don't think. Theoretically, right, like if you sit down and do back of the envelope calculations, you'd expect streaming to not be.
Hmm.
But these two runs with and without streaming are very different. And the funny thing is, the streaming is supposed to help for thin star formation, and here you see the one with streaming on top of the one without streaming.
Yeah,
So I think these gives you a bit of an idea of the variance, right?
you'll get very different wind properties here as well, so that would be interesting.
Yeah, that's right, yes. The alphas are very different.
Sorry, I didn't know what the question. Other questions? Are there any online, by the way?
Oh,
Not that I see, but we are about like 4 minutes over time, so I think it might be good to just have one more question if anyone has one. And then if anybody wants to talk with Sergio about all of these great results in more detail, feel free to sign up for a slot on the spreadsheet, which is in that email that I sent out earlier this week. There's lots of slots available this afternoon, so yeah, please do that if you'd like to. And I guess one last thing I'll say is that the student meeting as usual will be here at 3 p.m. So yeah.
okay.
It's
Okay.